it's different. Instead of methoxide, I'm proposing that the nucleophile in this reaction is methanol. Methanol does not have a negative charge. It's not a strong nucleophile, yet it does have on the oxygen unshared pairs of electrons that could be used to form a bond to a carbon. Now in this case, it's not strong enough to enter into the reaction, to cause the reaction to happen. Instead, what would happen, if anything, is the following. Methanol, as if it were not there, the organic molecule may spontaneously do this. It may spontaneously just lose the bromide anion. So if that were to happen, the product of that reaction would be this. The product of that reaction would be, and also the bromide would be lost. The product of that reaction would be a carbocation. Now, in principle, that carbocation, well, not just in principle, it is a highly reactive species. It has a positive charge. Organic fragments don't want to have positive charges. They want to quench that charge somehow. So in this case, the carbocation, in the presence of even a weak nucleophile, will look at that methanol and say, you'll do. You get in there, the negative charge or the electrons on the methanol would be good at forming a bond to that carbocation. So the product of this, if this worked out, and now we've got a new bond over here, make it blue because of the blue arrow, OCH3, it came with a proton, so that has a positive charge. The carbocation is quenched by the electron pair from the methanol. We have a protonated ether, and rather promptly that would lose that proton, and the product that would be formed would be 1, 2, 3. Down here, a bond, drop sideways, but a bond to OCH3, and at the same time, a proton would be liberated. A minute ago, I just suggested that in this molecule we're looking at, the 2-bromo-3-methyl pentane, that the bromide might spontaneously separate itself from the organic framework, forming a carbocation. This is unlikely. It is a process that doesn't happen quickly. Once it does form the carbocation, meaning of course that the carbon holds a positive charge, the carbocation is really a highly reactive species. Like a small set, carbocations, carbanions, a carbon with a negative charge, or carbon radicals, carbon with an unpaired electron. Those are unstable chemical species that do something quickly. Now, in this case, I glossed over something of kind of important, of great consequence. In this case, there's a carbon, a positive charge on a secondary carbon. Something can happen with that. Now, if we understand, let me draw in figures, we understand that there's a methyl group on carbon 3, but there is also unexpressed, because we don't usually show these things, there is a hydrogen. Every carbon is tetravalent, and if it's not expressed, if there's not a fourth bond expressed, then we understand that there's a hydrogen. We don't show those things. Now, something can happen here where is the following. If that hydrogen, the proton, and the pair of electrons recognize that there's a carbocation next door, a process that's called a hydride shift can happen. That is, the pair of electrons and the proton attached to the pair of electrons can migrate one bond away. So the effect of the hydride shift now, we understand that when the hydride shifted down to here, there's a hydrogen here and there's still a methyl group there. We don't usually show the protons. Well, the important thing is that the secondary carbocation, as a result of the hydride shift, has become a tertiary carbocation, and it turns out that a tertiary carbocation is more stable than a secondary carbocation. So given a chance for a simple thing, it turns out to be a simple thing, a hydrogen and a pair of electrons to migrate next to the next carbon, it happens real quickly. So in my earlier whiteboard, I suggested that that secondary carbocation hangs around long enough to react. It actually probably doesn't. It's probably much quicker that the hydride shifts, and the carbocation is a tertiary carbocation. So if now the weak nucleophile, I had shown methanol before that weak nucleophile had a chance to form a bond to a secondary carbocation, the secondary carbocation rearranged to become a tertiary carbocation. So by the time the slow methanol gets around to attacking the organic molecule, the nucleophile gets around to attacking this carbocation, it's there. So the reaction now, curved R would be that oxygen goes there. The result of that migration, the whole methanol molecule, I'll have to draw a little bit smaller here. We have a CH3 group here. We have the new blue bond down here to the HOCH3. That would now have a positive charge. And in a final step, in a quick step, that proton is lost, it bangs into a molecule of solvent, and in no time, the product now would be methanol, now bonded to it through the new bond, OCH3. So, all of this goes back to suggesting that if we have generation of a secondary carbocation, that secondary carbocation rearranges to become a tertiary carbocation. The tertiary carbocation would react even with a weak nucleophile. I give methanol as an example. The methanol attacks the carbocation. We have now what we would call a protonated ether molecule that rapidly loses its proton, and after the loss of the bromide, the rearrangement of the carbocation, we now have a product where the methoxide is bonded to a carbon that never even had a halogen in the first place. Carbocation rearrangements are something you cannot ignore.